Welcome to Lesson 24. Learn C programming on the Raspberry Pi. Okay, so last day we were looking at setting up an ultrasonic sensor, a range sensor, or some people call it a sonar. But today I want to go back to the C language and cover some more material that we'll need for later on. So I want to look at C operators. I have a table here on the screen that shows all of the operators that we use in the C language. And so I want to give some examples, some coding examples on how they work. But before I do that, let's just go over what some of these operators do and how this table works. So the first thing you'll notice is we have 1, 2, 3, 4 columns in this table. The first column is the precedence of the operator. So the precedence tells the C compiler which operators to evaluate first and which ones to evaluate second. So for example, I think one you might understand is the precedence number 3 here, which says that multiplication, division, and remainder operator, these 3 operators come ahead of adding or subtracting. So we do multiplication before we do addition or subtraction. So that's the way this precedence works, which means these increment and decrement operators, these guys take the highest precedence. They get done first. Although there is something that clouds the issue, depending on whether these operators are in front of the operand or behind the operand. In other words, whether they're suffix type or postfix type. But we'll get into that later on. So anyway, these operators here are all the highest priority type operators. If the compiler sees any of these, it tries to do them first. These next operators here on priority 2 tries to do them second. If you go all the way down the list, you'll see there's a comma operator. Yes, believe it or not, the comma is considered an operator, and it has the lowest priority. Priority 15, it's done last. Okay, so these are all the operators in the second column. The third column gives you a description of what the operators are. Okay, and well, just before we go on to that, I just want to mention here, here's an odd looking operator. It says size of. It's a word, but it's actually an operator. And we'll do examples of this later on as well. So we have the description column here, describes each of the operators, and then we have the associativity. In other words, how are the operators evaluated, left to right or right to left? Like for example, if I take something like, I'll just do this in Bash to show you in Bash how you can do it. All arithmetic in Bash, you can use the two round parentheses. So if I say in Bash 2 plus 3 times 6, one way you could look at this is you could say, well, 2 plus 3 is 5, and 5 times 6 is 30. Another way to look at this is 3 times 6 is 18, plus 2 is 20. And of course, because multiplication has higher precedence, the multiplication gets done first. Okay, so C works the same way as bash, or I should say bash works the same way as C. It observes the precedence rules of the C language. Of course, we can override that. In C, we can just put parentheses wherever we want. For example, I could put some extra parentheses in here just to say I would rather have the 2 plus 3 done first. Okay, so if you're not sure of what's happening in your C program, it might be a good idea just to put in parentheses everywhere to make the evaluation unambiguous. In other words, force it to go the way you want it to go instead of just guessing how it's going to go. Because it's not always true that operations always work the way you think they work. So this associativity says how it's evaluated left to right or right to left. Okay. Believe it or not, there are some computer programming languages that treat all operators with the same precedence, and they just evaluate right to left. So in those languages, for example, this 2 plus 3 or 2 plus 3 times 6, which gives us 20. In those languages, 2 plus 3 times 6 would assume that the plus and the times have the same precedence, but because they evaluate from right to left, the answer would come out to be from right. This is the right side. It would do 3 times 6 is 18 plus 2. So it's going from the right hand side to the left. If it worked the other way, if it went left to right, it would do 2 plus 3 and then times 6. Okay, so never make any assumptions. Always look up this table here to understand how C operators work. So let's go into Genie, and we'll try to give some examples. Okay, we'll need a small window here because it won't be that complicated. Here's our range program that we did the other day to work out the distance in centimeters to an object. Let me just close all these guys up because we don't need them anymore. And I'll create a new file here. Number sign inclu include .h. Okay. So we'll just do some some examples here off the top of my head. Let's start with let's just start, for example, with an integer I. And we'll set it to equal to, let's say, 3. Okay. So what would be the first example? Well, let's take something like this. Let's say we'll also have an integer j, and I won't initialize j to anything. I'll just say j is equal to plus plus I. We'll start with this example here. And then we'll say printf bracket, say j is %d and I is %d, new line, quote, comma, j, comma, I. and return 0. Boom. Okay, so let's save this in lesson 24 here. So I'll say save as, and okay, I need a directory here called lesson 24. Create a folder, dash 24, and I'll call this ex1.c. So for example 1.c. Okay, so this is example 1.c. And just close that all together. And we can make this window a little smaller here. Our examples today will be fairly short. Okay, so we'll go to lesson 24 directory, and we have this example 1, gcc example 1 minus o ex1. That's all we need, and we can say /ex1. Now you notice it says j is 4 and I is 4, which is kind of what we would expect. But let's change this now to we'll put the plus as on the other side here, like this. Okay, and now we'll save this guy, and we will compile it again and run it, and this time you notice that j is 3 and I is 4. So you're wondering, like, what the heck is going on? Well, if you look at this plus operator, this is the increment operator. There's two forms of it. We can have it either before the operand, so we could put the plus here, or we could put the plus on the other side. If the plus is on the left hand side, which is it is here, like this, then the plus will increment I first to make it a 4, and then assign it to j. And you notice the equal sign here. Maybe I should spread that out a bit here. The equal sign is an operator, and you see it's way down here. It's a priority 14. Simple assignment operator is the equal sign. It has very low priority, which means the plus gets done first. Okay, but this is where it's kind of a little weird, but you have to understand the way it works. When the plus comes in front of the operand, then it is done before the assignment. So I is incremented to here to a 4, and then it's assigned to j. When we put the plus after, then like this, then j is assigned the value of I, and then I is incremented. So it seems like what we're saying is that the equal operator takes precedence over the plus, which is way up here. But no, that's just the way C works, because this operator can come in front or after the operand. So there's two ways that guy can work. So I just want to clarify that. Be careful on using these increment and decrement operators. Okay. The other example I want to go over today is well, let's try doing some of these bitwise shifts, which I think are very interesting type operators. Let me give an example of that. I'll say I is equal to 3, and then I'll say, let's say j is equal to I, and I'll say left shift 1 bit. And I'll call this, let me save this as example 2. File, save as, and I'll save this as example 2. Okay, save. So look what we're doing here. We're saying that I is a 3 and j is not initialized, but j is going to be assigned I left shifted by 1. Well, if you look at I in binary, 3 in binary is, let's say 0000011, like that. And how many zeros we have depends on how long an integer is. Okay, so if we take that and we left shift it, so we're moving it to this side over here, then of course, if we left shift it, we get, let's see, 1 2 3 1 1 0. So you see how we moved that these two guys, we moved them over to the left 1 position, and the thing becomes 0 filled, so the trailing bit becomes a 0. So that's a left shift, and of course that's equal to 6. So if we ran this program, we'll save it, and we will compile it. And we'll say ./ex2, then you see j becomes 6. So you can see what a left shift does. Okay. What's interesting here is that a left shift of 1 is the same as multiply by 2. I'll say that again. A left shift of 1 is the same as multiply by 2. So if I was to left shift it 2 binary digits to the left, then I'm going to end up with a 1 here and a 0. So that's now moved over 2 places. So remember, what did I say? A left shift of 1 is multiplied by 2. So a left shift of 2 is multiplied by 4. So instead of 6, we should get 12. Let's save this guy. Try it again. Compile. And we get j is 12. Okay. So whenever you want to multiply something by 2, 4, 8, 16, 32 or something like that, you can speed things up just by using left shift. Of course, the complement of that is to do a right shift. So if I said, for example, let's say j is 3, well, let me do a right shift first of 1. Right shift of 1. And I'll take that out. So if I take a 3 and I right shift it by 1, 1 2 3 4 5 1. You notice this first 1 here just drops off. Well, it seems like that's a natural thing to do. Let's check it out. And we end up with j is equal to 1. and I is still 3. Okay? So a right shift of 1 is equivalent to divide by 2. A right shift of 2 is the same as divide by 4. So a right shift or a left shift, you can always do that in place of multiply or divide if you want to get a little bit of speed out of your C program. Okay? By the way, all of these things you can try right in Bash just by using this. I can say, for example, 3 right shift 1, and it says it's a 1. So instead of writing a whole main program here with all of this to try it out, I can just do this command in Bash and I get the same result. I get a 1. If I wanted to shift it the other way in Bash, I could just say left shift and I get the answer is 6. Okay, so that kind of looks at this plus plus minus minus, these increment decrement, and also these shifting. Okay, but we also have some other kind of bitwise operators. Whenever it says bitwise, it means it's working on bits, not on bytes. So here's another one, bitwise AND. Let's try that. So I'm going to say I is 3, and let's say j is going to be, I'll set j equal to 4. So 3 is that, and then comma 4 is that. So now we'll say, let me get another one in here, int ijk. So now we'll say k is equal to, and we'll say I bitwise and j. So j is that, I is that. Let me add one more, and k is %d. So j, I, and k. And this one, I'll save this one as example number 3. Let's put a 3 up there. Okay, so I have a 3 saved. I can now say cex3.c minus oex3, and then I can say /ex3. Well, just before we run it, let's look what we have here. We have this, which is a 3, and this is a 4. And if we do a bitwise AND, then that means we are going to AND this 0 with a 1. And we are going to get a 1. Then we're going to AND this second 0 with the second 1. Oh, actually doing an AND. Sorry, we're going to get zeros. We're going to get zeros. Maybe I should write down the precedence table here. Let me make a new file here. So let's say let's look at the AND table. The AND. So if we say A, how am I going to do this? B space. Now we'll say A and B. I'll do it like this. So if A is a 0 and B is a 0, then A and B are zeros. If A is a 1, B is a 0, then A and B is a 0. If A is a 1, or let's say a 0, B is a 1, then A and B is a 0. And if A is a 1 and B is a 1, then A and B is a 1. So this is the AND table. I don't think I need that. Okay, that's an AND table. So you just have to memorize these tables. If you don't know them, then you have to memorize them. So let me change this guy now to an OR table. So I'll put the vertical bar here as an OR, and the difference is that this is going to be a 1 and this is going to be a 1. So with an OR table, A is a 0, B is a 0. You have a 0 as the result, A or B. With A is a 1, B is a 0, A or B is a 1. A is 0, B is 1, the answer is 1. And if A and B are both 1, then the answer is 1. So there's one more table that I want to show you, and you have to memorize them, learn them. And I will just take this guy, I'll paste it down here, and this one is going to be exclusive OR, this little caret symbol, exclusive OR. Because what I showed you before, the vertical bar is the inclusive OR. So exclusive OR works almost the same as an inclusive OR, except that this last one is a 0. So the only way to get a 1 is to have a 1, 0, or a 0, 1. So that's why they mean exclusive. It excludes this last combination here, whereas inclusive includes this last combination. Okay, so why don't we just save this guy here, save it as, we'll just call this logic.txt. Oh, folder, lesson 24. Save. Okay, so now let's go back to our example 3. When we said we're doing an AND here, then 0 and 1. See, we could actually put them, I could put it down like this. Let's say, and I could move it over like that. So now when I go 0 or 1 here and 0, the answer is going to be 0. So let me put another comment there. And I'll go here. It will be 1, 2, 3, 4, 5, 6. Okay. And the reason they're all going to be 0 because the AND, the only way I can get a 1 is if they're both 1s. So the answer here should be 0. Okay, so let's try this with EX3. I want to compile it again here, just in case I made a mistake. And you see K is 0. K is 0. But if we do an OR, inclusive OR, with the single vertical bar, wherever that is, right here, and save it, then we should end up with 111, which is equal to a 7. Well, let's see if that's true. Compile it again and execute, and now K is equal to a 7. Well, the last example is on using a bitwise exclusive OR. But in this example here, I think we're going to get the same result. Let's save it, and if I compile it and I run it, we get the same result. K is 7. But if I changed, for example, the 4 to a 5, J is a 5. So here we have a 5, which means we have a 1 here. Then on an exclusive OR, this first one and this first one are going to give me a 0 here. So everybody follow that, and then my answer is going to be 6. Well, let's see if that's right. And I go here, compile, and you see my answer now is 6. And by the way, of course you can do all of this, practice it using bash on the Pi. You can say, what was the first example? We said 3, well, this example here says 3 exclusive OR 5, which gives us a 6. Or we could say 3 OR 4 gives us a 7. So you can try all these out in bash as well. Okay. Okay, so that's kind of going over some of the little crazy type operators. The other one I just wanted to quickly mention was size of. So let's do an example here. And what I'll do is I'll say int, well, let me get rid of all this stuff here. I'll say int I is equal to 3, float j is equal to 4.2, and so I'll say I is equal to, or no, say let's say size of I is %d, and size of j is, and what I'll do here, I don't need k in here, so I'll use the size of operator. So the size of I is %d, and better change that to an I, and then the next one is going to be the j, like that. So size of I %d is going to be this. Now the key word size of doesn't look like a single character. It doesn't look like any of these other characters. Well, there's some odd ones in here, but we're just looking at size of right now. I mean, you can think of it this way, is they just ran out of crazy characters to use on a standard US keyboard. Remember, C was created around 1970. So, you know, what is it, 47 years old now? And can you imagine what the keyboards were like 47 years ago? Well, you probably can't, but I can. Anyway, if you had a special character, like maybe, I don't know, maybe the @ sign or something, I don't know, they could have used some other character, but they didn't. They just used the word size of. Okay, so let's save this guy as, I'll save it as, I'll I'll save it as example 4. Oops. 4. And now I'll just compile it. Oh, GCC, sorry. Oh. What am I doing wrong here? Oh, I'm missing a parenthesis at the end here. Okay, save that guy. Try it again. And /ex4. And now you can see size of I is 4 and size of j. That tells you how many bytes each one of those variables is. Now if I put in here another one, let's say double k equals 2.1, for example, then I could also put in here printf quote size of k is %d/n quote comma size of k. Okay, so now we can add in, we made a double. Double is basically a float that's just twice as long. So it has more precision. More precision means more decimal points. So I can compile this guy again, and we can run it, and you see size of k is 8. If I wanted to, I could even add another one in here. I could say long long akl l equals 5. Oops. Say 5. And then I could put in another print here for L. Size of L is size of L. And let's see, compile this guy. And compile it again. Oops. Another mistake, forgot a semicolon at the end. And save it. Try it again. And you notice, oh, size of L is 4. So that's the same as a regular integer. How about if I do this? Long. And run it. And now size of L is 8. Okay. So you'll find a lot of these in C where you can change how much precision you want for these pieces of data. Of course, for a character, let's try the last one. Character X equals, let's say, the letter J. And I'll put that in here. For a single character, size of X is size of X. Save, go down here, compile, and run it, and you see size of X is 1 byte. Character is 1 byte. Okay, well, that's all we're going to do today. Make sure that you memorize these 3 tables and look at the full precedence table here, or the operator table. Go through all of them, try to understand them, practice with them, write little pieces of code like I did to work things out. And also, lastly, play with Bash. Learn a little bit of Bash on the side here to see how things work in Bash, because you'll find in Bash you can do things a lot quicker if you're just prototyping, and you can see the result, what the results would be, and compare them to C. Alrighty, so that's lesson number 24, and I'll see you next time for lesson number 25.